Hello everyone and welcome to another new lecture. Today we will be studying one of the more important topics in algorithms, and that is dynamic programming, or DP for short. Many mistake DP for divide and conquer, but there are a few differences between the two. In fact, DP is better than divide and conquer in terms of computational complexity, and we will see why today. We will understand how DP works through three examples, namely rod cutting, matrix chain multiplication, and longest common subsequence. This lecture covers chapter 15 of the main reference book. Let us first see what was covered in our previous lecture. We studied about binary search trees that are used to store, delete, and search keys using a binary tree data structure. We also saw that the operations all are proportional to the BST height, and for a given subsequence of keys, there are many BST representations depending on the key that is chosen as the root. Finally, among all operations, deleting a key required more concentration as it had to be done while maintaining the BST property. The dynamic programming that we will be studying today is mainly applied to optimization problems. It means that if a given problem can have many possible solutions, we then can use DP to find the solution which is the most optimal. By optimal, we mean that the solution that gives us the best value for the problem in terms of what we define as the problem objective. The word programming in dynamic programming does not mean coding, but rather refers to storing the solutions to subproblems in a table and reusing these solutions when the subproblem is encountered again, without the need to recompute that subproblem. So, if we compare DP with divide and conquer, we see that in contrast to divide and conquer algorithms that partition the given problem into disjoint subproblems, DP applies when the subproblems are not disjoint but instead overlap. That is, subproblem share sub-subproblems. So in such a scenario, the divide and conquer would repeatedly solve the common sub-subproblem, therefore doing more computational work. DP, on the other hand, solves each sub-subproblem only once and stores the solution to this sub-subproblem in a table to avoid the effort of recomputing it again when the same sub-subproblem appears later on. Typically, a DP algorithm development has four steps. Firstly, we should characterize the structure of an optimal solution. Next, we then should define the value of the optimal solution in a recursive manner. Then compute the value of an optimal solution, and finally, construct an optimal solution from the computed sub-solutions. Do not be terrified by these four steps. Once we see some examples, you will see how easy the concept is if formulated properly. Our first example is the rod cutting problem. Suppose you own a company that makes rods and sells them. Your company now wants to update its business plan by providing a new service called rod cutting to satisfy demands from other companies. What is rod cutting? Given that your company produces rods, each of length n inches, you want to maximize the revenue you gain by selling these rods in different lengths. That is, you have a price Pi for each rod of length I inch, and you want to see how to maximize the total selling price of the rods of length n inches. Let's assume that this is the price list you have for different lengths of the rod, which has a maximum length of 10 inches. So a rod of length 1 inch would cost $1, a 2-inch rod would sell for $5, and so on. In this problem, the task of cutting a rod of length n into smaller pieces is free, and the length of each rod or pieces of it is assumed to be an integer value. Now, if the price Pn for a rod of length n inches is large enough, then you would not bother to cut it into smaller lengths, as P of n would be the optimal solution. If we look at the price list on the previous slide and consider n is equal to 4, we see here that there are 8 ways to cut up a rod of length 4 inches. The numbers written above each cut of the rod refers to its price in dollars. So if the rod is not cut at all, it would return a revenue of $9 as shown in figure A. If it is cut into a 1-inch and 3-inch rod, it would cost 1 plus 8, which is equal to $9 as shown in figure B. We do this for all the 8 cases. We see in figure C, if we cut the 4-inch rod equally into two 2-inch pieces, the total cost would be $10. This is more than the price of an intact 4-inch rod, which was $9 as shown in figure A. Therefore, our optimal solution would be to cut the 4-inch rod into 2 halves because it maximizes our revenue. We saw that any rod of length n inches can be cut up in 2 to the power n minus 1 different ways. So we independently decide to cut or not to cut the rod at some length I, starting from the left end of the rod. Here, I takes values starting from 1 to n minus 1. In this example, suppose we have a rod of length 7, and the optimal decomposition would be cutting it into 3 pieces. The first of length 2 inch, the second of length 2 inch, and the third of length 3 inch. So this indicates that the rod of length 7 is cut into 3 rods of length 2, 2, and 3 inches. To formulate it, we can say that if an optimal cost is obtained by cutting the rod into k pieces, where k takes values from 1 to n, then an optimal decomposition of the n value would be I1 plus I2 plus all the way up to Ik. Here, I1, I2, and Ik are lengths of rod pieces 1, 2, and up to k starting from the left end. Since the above decomposition is optimal, its corresponding revenue, denoted by Rn, can be obtained by summing up the price for each piece of length I1, I2 up till Ik. So these prices are denoted by Pi1, Pi2 up till Pik. In our example, where we have rods of maximum length 10 inches, the optimal decomposition can be determined by inspecting the revenues obtained for all values of n from 1 to 10 as shown over here. So R1 corresponds to the maximum revenue of a 1-inch rod, which according to the table is $1. For a 2-inch rod, the optimal cost is $5 and does not involve any cutting. The same is for a rod of length 3 inches. For n is equal to 4, we see that R4 is equal to 10 and is obtained by cutting the rod once into 2 halves. So I1 is equal to I2 is equal to 2 inches, each costing $5. Therefore, the general equation to calculate R of n is given as such. It is the maximum of the price of the rod of length n and the sum of the revenue of a 1-inch rod and a rod of length n minus 1 inches, and the sum of the revenue of a 2-inch rod and a n minus 2-inch rod. This goes up to the sum of the revenue of a rod of length n minus 1 and a 1-inch rod. Note that the second argument, this, and the last argument, this, are the same. In the equation for Rn, observe that the first argument Pn is the cost of selling the rod without any cuts. The remaining n-1 arguments yield the maximum revenue obtained by making a cut that divides the rod into 2 pieces, one of length I and the other of length n minus I. The question now is that what is the best I value at which we should make the cut in order to maximize our revenue? Answer: we have no prior information on that. So we should do what is known as a brute force computation, that is, consider all the possible values of I, compute the revenue, and then choose the maximum revenue. So to solve the original problem, we need to break the problem into smaller problems and solve them to get the original solution. That is why we say that the solution to the original rod cutting problem is optimal only if the solution to its smaller subproblems are optimal and are obtained independently. Therefore, we want to ensure that the rod cutting problem does indeed have an optimal substructure. Now, let's try to improve the recursive equation for obtaining the revenue that was shown on slide number 8. What I mean by improving it is to look at the decomposition part differently. Instead of summing up two revenue values in the equation, let us replace the first revenue computation with its actual price, Pi. In other words, we calculate the revenue by decomposing the rod of length 10 inches into a fixed first piece, followed by the recursive revenue equation for the remaining part. So the revised equation for Rn would look like this. By doing so, we have reduced the calculation complexity by only requiring the equation to calculate the solution to one subproblem, that is the second term, rather than two subproblems. The first term over here is fixed and does not need to be calculated. Now let us look at the top-down implementation of the rod cutting problem using the improved recursive revenue equation we saw in the previous slide. The reason why it is called top-down is because we start calculating the revenue from the actual length, that is n, and break it down as we move on. In this pseudocode, the algorithm takes as input the price list for all n elements and the value of n. Once n reaches 0, it stops. Until then, it iterates from I is equal to 1 to n to calculate the revenue for all possible cut lengths I. Running this code for large values of n becomes very time-consuming, and we will see why in the next slide. Again, let's go back to our n is equal to 4 example to show why the top-down approach is not efficient. For n is equal to 4, the problem breaks down into the following tree using the recursive equation we obtained for Rn. In the first iteration of the for loop, when I is equal to 1, we call the cut rod procedure recursively on n is equal to 3. In the second iteration, we calculate the revenue for n is equal to 2. In iterations 3 and 4, we call the procedure recursively as shown over here. Do you find any overlapping computation here? Yes. We see that these two subtrees actually are the same. So we have done redundant work by calculating the same revenue repeatedly. This happens because we are unaware of the fact that the subproblems in this example actually share the same subproblems. Now you can imagine what would happen if the value of n grows large. Then we would have many overlapping subtrees and therefore would have done a lot of unnecessary computation. As I mentioned at the very beginning of this lecture, DP applies when the subproblems are disjoint. But so far we have seen that the subproblems do overlap. Therefore, the top-down approach should be replaced with a more efficient DP approach where each subproblem is solved only once and stored in a table so that if the same subproblem appears again, we can look up the table and use the value we stored there rather than recompute the subproblem again. While DP saves computational time on one hand, it imposes the need for additional memory space on the other for storing the table. So there is a trade-off between time and memory over here. There are two ways to accomplish this using DP. The first is modifying the same top-down approach by including the capability to store the solutions of subproblems. This is known as memoization. So when we say that the recursive procedure has been memoized, it means that the results of the subproblems have been saved in a table and the procedure can access these results that have been computed earlier for future use. The second approach is a bottom-up approach where we source the subproblems by size and then solve them in the order of smallest to biggest size value. Since we start with the smallest size subproblem, we know the solution to any larger problem can be easily obtained as it depends on the previously solved smaller problems that have been stored. Let's look at the memoized top-down approach first, the pseudocode of which is shown here. We define an auxiliary array R to store the values we compute as the memoization process. Initially, we set all the elements in R to a low revenue value of -infinity. Then we call the memoized cut rod auxiliary procedure on P, N, and R. We first check to see if we have the optimal solution for N in the memory R or not. If yes, we return it back to the memoized cut rod procedure here. Otherwise, we follow the same procedure as we saw in the earlier top-down procedure with only one difference. On line 8, shown here, we store the value of the calculated revenue in the array R for future use. Here we see the bottom-up DP implementation of the rod cutting problem. Again, we need to store the optimal solution of each subproblem, so we define an array R of size n. Obviously, R0 is equal to 0 as no effort is needed to cut a rod of size 0. By iterating over all n values in the for loop in the increasing order of size given on lines 3 to 6, we use the same approach used in cut rod procedure for a particular j value, except that line 6 can directly access the optimal solution in the array for entry j minus I instead of the recursive call to solve the subproblem of size j minus 1. So far, we saw the example of rod cutting using DP. So if you want to compare the running times of the very first cut rod procedure, it would exhibit an exponential running time because it considers all possible 2 to the power n minus 1 ways of cutting up a rod of length n. So T of n would be of the order of 2 to the power n. In the DP version, however, both the memoized top-down and bottom-up methods have the same asymptotic running time of theta n squared. This is due to the two nested for loops, which compared to the cut rod procedure is more efficient. Now let's consider another example called matrix chain multiplication. In this problem, we are given a sequence of n matrices, namely A1, A2, A3 up till AN. And we want to find the final product of these n matrices. From the multiplicative property of matrices, we know that matrix multiplication is associative. That is, no matter how you parenthesize the matrices for multiplication, the final product will always be the same. So a product of matrices is fully parenthesized if it is either just one single matrix or it is a product of two fully parenthesized matrix products surrounded by parentheses. To understand this more clearer, let's take a look at this simple example where we want to multiply four matrices A1, A2, A3, and A4. To do so, we first try to fully parenthesize them. So how many ways exist to fully parenthesize these four matrices? Given four matrices, there are 5 ways to fully parenthesize them as shown here. Interestingly, the way we parenthesize the matrices substantially impacts the cost incurred in calculating the product. To understand how, let's first try to find the cost of multiplying two matrices. Here, we do not consider square matrices, but a more general case where it can have any dimension. So, we have seen how to multiply two square matrices earlier when studying divide and conquer. Now, let's take a look at a generalization of that pseudocode which works for non-square matrices as well. As seen earlier, two matrices can be multiplied using three nested for loops as long as the dimensions match or are compatible. That is to say, we can multiply two matrices A and B if and only if the number of columns in matrix A is equal to the number of rows in matrix B. So if A has dimensions P and Q and B has dimensions Q and R, then their product would be some matrix C of dimensions P times R. Moreover, the main cost to calculate the elements in the final matrix C corresponds to the number of scalar multiplications that are executed in line 8 of the pseudocode. So for two matrices A and B with the given dimensions, there would be P times Q times R number of scalar multiplications. Fully parenthesizing matrices efficiently can therefore dictate the number of scalar multiplications that are performed. To show how the choice of fully parenthesized matrices can impact the total number of scalar multiplications, consider the three matrices A1, A2, and A3, where A1 is of dimension 10 times 100, that means it has 10 rows and 100 columns. A2 is 100 times 5, and A3 is 5 times 50. There are only two ways to fully parenthesize these three matrices. These two are shown over here. In the first parenthesization, the product of A1 and A2 is computed first. The product of these two matrices is then multiplied with A3 to give the final solution. Since A1 is multiplied to A2, we will have 10 times 100 times 5 number of scalar multiplications here. The result of this product is some matrix of dimension 10 times 5, which when multiplied with A3 results in 10 times 5 times 50. Therefore, the total number of scalar multiplications would be 10 times 100 times 5 plus 10 times 5 times 50, which is 7,500 number of scalar multiplications. Doing the same for the second case would yield 75,000 scalar multiplications. Comparing the two, we see that the first parenthesization option is 10 times faster than the second. Now that we have understood the problem, let's try to define it formally in the next step. The formal problem statement for matrix chain multiplication is as follows. Given a chain of n matrices, where the dimension of some matrix, say AI, is denoted by pi minus 1 times pi, fully parenthesize the product A1 times A2 times dot 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 times AN in a manner that minimizes the number of scalar multiplications. So we have to find the order in which the matrices should be parenthesized so as to give us the lowest cost in terms of scalar multiplications. Before looking at the DP solution to this problem, let us see what happens if we exhaustively check for all possible parenthesizations. To do it the exhaustive way, we begin by counting the number of parenthesizations for a chain of n matrices. Let's denote this number by P of n. Therefore, if we have one matrix, there is only one way to parenthesize it, and that is A of 1 with parentheses. If n is equal to 2, then we again have only one way to pairwise parenthesize it, and that is A1 times A2, and putting both of them in a parenthesis. For n is equal to 3, we would have two options. We can say A1 times A2, this in parentheses, times A3 and the whole thing in parentheses, or we could have A1 dot in parentheses A2 dot A3 in parentheses, whole thing in parentheses. For larger values of n, a fully parenthesized matrix product is the product of two fully parenthesized matrix subproducts. The split between the two subproducts, however, can occur between the kth and the k plus first matrices, where k takes values from 1 to n minus 1. This can be recursively expressed as follows. And the solution to this recurrence is exponential and is given by omega 2 to the power n. As an exercise, try to prove that this is the solution to this recurrence. So calculating all possible parenthesizations for the sequence of n matrices has an exponential running time, thus making the brute force method of exhaustive search a very poor strategy to find the optimal parenthesization. Now it's time to look at the DP approach to this problem. We will gradually explain the process by following the 4 steps we mentioned at the very beginning that define the DP approach. In step 1, we need to define the structure of an optimal parenthesization. That is, we should find the optimal substructure first and then use it to construct the optimal solution to the original problem. Suppose we have already evaluated some subchain of matrices, say AI to AJ, where AI dot dot J represents this subchain as shown over here. Now, let us assume that the optimal parenthesization of this subchain requires us to split the product between two matrices AK and AK plus 1, where K takes values from I to J minus 1. So this means that now our subchain Aij, which was denoted over here, has been split into two, where we have AI times AI plus 1 times dot 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 times some AK times some AK plus 1 times dot 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 some AK. So the split happens over here. So now we have a sub-subchain, and this sub-subchain, that means from AI to AK, would be the prefix of the subchain Aij. Therefore, we can say that the subchain AI to AK is actually optimally parenthesized. Why? Because we assume that AI to AJ has an optimal parenthesization if the split is between AK and AK plus 1. So AI to AK is a sub-subchain of the optimal parenthesization of AI to J. So for the sub-problem to be optimal, its sub-sub-problem should also be optimal. A similar argument holds for the sub-subchain AK plus 1 to AJ. That is, this sub-subchain should also be optimally parenthesized. Using this optimal substructure, we are now ready to derive the optimal solution to the original problem in a recursive manner. This brings us to step 2 of the DP formulation, that is deriving a recursive solution. We begin by defining a few variables. Let us denote by Mij the minimum number of scalar multiplications that are needed to compute the matrix chain product Aij. So for the full problem, where we have n matrices, the lowest cost to compute AIn would be given by M1n. With this definition, we can now use recursion to compute the cost. So if I is equal to j, that is the chain consists of only one matrix, then no scalar multiplications are needed. Therefore, m of I would be equal to 0. But if I is less than j, then we make use of the optimal substructure that we defined in step 1. In other words, we say that to optimally parenthesize the chain AI to AJ, we need to split the product Aij between matrices AK and AK plus 1. By doing so, we see that Mij would essentially hold the minimum cost for computing the subproducts Aik and AK plus 1j, as well as the cost of multiplying these two subproducts together. So the number of scalar multiplications involved in multiplying the subproducts aik times ak plus 1j would be pi minus 1 times pk times pj, where the p's are defined as dimensions in the earlier slides. Putting this in a mathematical form gives us this. Therefore, the minimum number of scalar multiplications for the chain AI to AJ would be the minimum number of scalar multiplications for the subchain AI to AK and the subchain AK plus 1 to AJ and the product of these two subchains. This recursive equation, however, assumes that we know the K value of the optimal split, but in fact, we do not know this value. So, since we do not know the point at which to split the matrix product chain, we have to now check for all possible K values that result in the optimal parenthesization. Let's look back at the values that K can take in the chain A, I, J. Over here, K can be after AI or AI plus 1 and so on up till AJ minus 1. Therefore, there are j minus 1 minus I plus 1, which is equal to j minus I possible values for k. Now that we know the range, let's update the recursive equation on the previous slide as follows. That is, m of ij can be calculated as shown here. When I is equal to j, that is when there is only one matrix, mii would be equal to 0. Otherwise, when I is less than j, we have to calculate the previous equation for mij for all possible k values, that is from I to j minus 1, and choose the minimum value as the cost. The value of k that returns the minimum cost is stored in another two-dimensional array at Sij. Similar to what we did in the rod cutting problem, let us now draw the recurrence tree for the minimum cost of the chain A1 to n, denoted by M1n, considering all possible values of k. So k can have values from 1, 2, up till n minus 1. So if k is equal to 1, it means that we split the chain A1 to n into A1 to 1, which is basically the single matrix A1 and the subchain A2 to n. If k is equal to 2, the two subchains would be A1 to 2 and A3 to n. If k is equal to 3, the two subchains would be A1 to 3 and A4 to n. In this tree shown over here, we see that M3 to n, shown in red, is repeated twice, and M4 to n, shown in green, is repeated 3 times. This clearly indicates that we are computing the same subproblem repeatedly, thus increasing the running time to an exponential order. This is where DP sweeps in. We can use the bottom-up DP approach with memoization, as shown in this pseudocode, to obtain a more reasonable running time by avoiding repetitive computations. The pseudocode is called matrix chain order, which takes as input the list of the dimensions of the matrix chain A1, A2 to AN. So the length of the list, or array P, is n plus 1, as shown over here. To store the minimum cost of scalar multiplications and the optimal k value for the split, we define two tables or two-dimensional arrays M and S on line 2. The array M is a square matrix of dimension n and S of dimension n minus 1. In the first iteration of the outermost for loop on line 3, Mi, I plus 1, is computed for chain lengths of 2, that is L is equal to 2. In the next iteration, it computes the minimum cost of chain of length 3, and so on. Finally, it stores the optimal M and S values and returns them. Note that for the matrix chain A, I to J, there are J minus I plus 1 number of matrices. The cost of the product of this chain is a function of the cost of the products of its subchains, which involve lesser than J minus I plus 1 matrices. So if K is the split point for the chain AI to J, we would have two subchains, AI to K and AK plus 1 to J. The number of matrices in the first subchain, that is AI to K, is K minus I plus 1, which based on the value that K can take is less than J minus I plus 1. Similarly, the second subchain, A K plus 1 to J, has J minus K number of matrices, which again is lesser than J minus K plus 1. With this said, we see that the DP algorithm fills in the table by solving the parenthesization problem for smaller subchains first and then increasing the length of the chain. Let's see this in action using a matrix chain of 6 matrices. Since we are only interested in the values of I less than j, we do not include the entries for the values I greater than or equal to j in the table M. So in this table, we have the 6 matrices that we want to multiply and their corresponding dimensions. The M and S tables are also shown over here. They have been rotated so as to eliminate the diagonal and remaining part of the table which are unimportant. In the M table, I and J take values from 1 to 6 as we see over here. So the cost for single matrices A1, A2, A3 up to A6 are all 0. The cost of multiplying the chain A1 to 2 is shown over here. That means it is the product of A1 and A2, and it is obtained by multiplying 30 times 35 times 50, which is 15,750. In this way, we can now fill up the entire table till we obtain the cost for the chain A16, which is 15,125. The corresponding K values that result in optimal parenthesization are also stored in table S. For instance, we want to calculate M25. That is the product of the chain A2 to 5. The chain can be split at K is equal to 2, K is equal to 3, and K is equal to 4. Therefore, we will have 3 possible parenthesizations as shown here. Calculating the cost for each case tells us that the minimum cost is obtained if we split at K is equal to 3. That is 7,125. This value K is stored at S25, which is here and here. So we have K is equal to 3. As an exercise, I want you to work out the cost for M15 given these 5 matrices. I have already done it for you up till M13. Our final example deals with a very common application called longest common subsequence, or LCS for short. One immediate application that comes to mind is genetic sequencing in biology, where it is required to compare the DNA strands of 2 different organisms. We know that each DNA strand comprises of 4 bases, namely adenine, guanine, cytosine, and thymine. For short, they are represented by the alphabets A, D, C, and T respectively. So if S1 is the DNA strand of organism 1 and S2 is that of organism 2, we want to find the longest subsequence similar in both strands. Such a comparison of the 2 DNAs tells us how closely the 2 organisms are likely to be related.
There are various definitions for similarities between S1 and S2. In LCS, however, we are interested in finding a strand S3 such that the bases that appear in S3 should appear in S1 and S2 and in the same order. It is not necessary for the bases to appear consequently. Here, only order is most important. Going back to the strands S1 and S2, we see that the longest strand is what we have over here. To give the LCS problem a formal look, we define it as here. Given two sequences X and Y, we aim to find common subsequences of X and Y that have the maximum length. For instance, if X is as given here and Y is as given here, then the sequence BCA is a common subsequence of both X and Y. But this is not the longest common subsequence. The longest common subsequence, indeed, is of length 4 and is BCBA. Some of you might have also noticed that there is another LCS of length 4 between X and Y, and that is BDAB. Can you find any more? Now that the LCS problem is clear to us, let's follow the 4 steps in the DP formulation of the problem. As step 1, we need to characterize the LCS problem. To see how this should be done, we need to first understand the inefficiency of the naive approach to solving the problem. The sequence X contains m elements, x1, x2 up to xm. This is similar to a set with m elements, as shown over here. We know that for such a set, there would be 2 to the power m subsets. Therefore, sequence X, if represented as a set, would have 2 to the power m subsequences and thus requires exponential time. So we need to find an optimal substructure property for LCS to make it more efficient to solve using DP. Now, let's look at this optimal substructure property. For sequence X, given here, which has m elements, let x of I be defined as the ith prefix of x, where I can take values from 0 to m. So, if we define a prefix xi, it corresponds to a subsequence of x, which includes the first I elements of x. For example, if x is equal to a, b, c, b, d, a, b, then the prefix x4 would be the first 4 elements of x, which is a, b, c, b. And x0 would represent the empty sequence. Now, with this definition of prefix, we arrive at a very interesting theorem. The theorem states that for two sequences, x and y, as defined over here, let Z be any LCS of x and y where the subsequence Z has k elements. Under such situation, there would be 3 cases that may occur. First, if the last element of sequence X, which is xm, is equal to the last element of sequence Y, which is yn, then the last element of subsequence Z, which is zk, would be equal to x of m, which is in turn equal to y of n. As a result, this would imply that the prefix zk-1 is an LCS of the prefixes xm-1 and yn-1. Or, if the elements xm and yn are not equal, and the element zk is not equal to xm, then this implies that Z is an LCS of prefix xm-1 and the sequence Y. Or, if elements x of m and y of n are not equal, and zk is not equal to y of n, then this implies that Z would be an LCS of the sequence X and subsequence yn minus 1. The proof of this theorem is given on page 392 of your textbook. So I recommend you to take a look at the proof. Note that in the first case of the theorem, we examine two subproblems. That is the prefixes xm-1 and yn-1. In the other two cases, however, we examine only one subproblem. That is either xm-1 in case 2 or yn-1 in case 3. Observe that since we check for all possible prefixes, it is guaranteed that one of the optimal subproblem solutions will appear as an LCS of sequences x and y. For the first case, where element xm is equal to yn, we compare the prefixes xm-1 and yn-1 and add 1 to the LCS resulting from this comparison. In the remaining two cases, the subproblems may overlap. This is because to find an LCS of x and y, we need to find the LCSs of x and yn-1 and xm-1 and y. These two comparisons, however, involve subproblems that find the LCS of xm-1 and yn-1. Putting this in a mathematical form, we define Cij as the length of an LCS of prefixes xi and yj. So, if I or j is equal to 0, it means that one of the sequences is empty, and thus the resulting LCS is of length 0. This is the first case. If I and j are positive, and the element xi is equal to the element yj, then the LCS has a length of the LCS resulting from the prefixes xi minus 1 and yj minus 1 plus 1. If I and j are positive and the elements xi and yj are not equal, then we return the maximum value stored by comparing the prefixes xi and yj minus 1 and xi minus 1 and yj. Based on this equation, we can easily write an exponential time recursive algorithm to compute the length of an LCS of the two sequences. Now, let's use dp to compute the solution in a bottom-up manner as step 3. The procedure defined here is LCS length, which takes the sequences x and y as inputs. It uses a table C of dimension m plus 1 times n plus 1 to store the length of LCSs found and fills the rows of the table from left to right. In addition to table C, it also uses a table B of size m times n as auxiliary memory to help in the calculation of the solution of the subproblems. Eventually, upon execution, the procedure returns these two tables. Therefore, the value stored in CMN would basically be the length of a longest common subsequence of the two sequences x and y. The pseudocode for LCS length is given here. On line 3, we define the tables C and D. On line 8 onwards, we apply the three cases and store the lengths of the LCSs found in each iteration. The arrows stored in the B table, which is on line 12, 15, and 17, help us visualize and trace the LCS as the algorithm runs. Because of the definition of prefix, the LCS problem would have only m times n distinct subproblems, which contributes to the running time of the LCS length procedure, as we see over here. Filling up the tables takes constant time and is therefore negligible. In this example, we have the sequence X with 7 elements and sequence Y with 6 elements. So we have to use a C table with 8 rows and 7 columns, and write the elements in each of the sequences as shown here. Always begin from the lower right corner of the table. This is because we start by comparing the last elements in the two sequences. So start from the element C76. The last element of sequence X is B, and of sequence Y is A. They are not equal. Then we apply case 2, which states that compare X6 and Y, which is A and A. Since they are equal, we now compare C5, 5, and so on. You place a diagonal arrow as shown over here in a house whenever the two elements of the two sequences match. This helps you backtrack and determine the LCS once you are done. That is, when you reach a house of value 0. The arrows that we have seen so far in the example are stored in the B table. In the example, we place it in the C table for sake of demonstration. The marking of the arrows, however, give you the LCS in the reverse order. To print it out in the correct order, if you want to implement the procedure LCS length, you will need to use the procedure called print LCS as shown next. The procedure takes as input the B table, the sequence X, and the lengths of both sequences X and Y. If they are empty sequences, it exits. Otherwise, if it sees a diagonal arrow, it recursively calls itself with length I-1 and j-1 as inputs. This is case 1 of the theorem. Otherwise, if it is an upward arrow, it calls itself with length I-1. Otherwise, it passes length j-1 if it is a horizontal arrow. Applying this procedure on our previous example would therefore print the LCS BCBA.